Now that plastics insulators have taken much of the waywardness out of experimental work in electrostatics, we can go ahead with rather more confidence than in the past. We're going to show you one or two of the less familiar demonstrations which you in turn might like to carry out in class. First, we think it important to show that the gold leaf electroscope measures the electricity in ordinary use as well as the less familiar static electricity. Because the deflection of the electroscope varies with the square of the voltage, the deflection can record an AC supply as well as a DC. Faraday himself used this sort of experiment to show that the current flowing in circuits was a current of what had long been called electricity. But he ran into some trouble with the experiment I'm going to show you now. I am going to give my colleague, Martin Harrop, a charge when he stands on this insulated stool. If I put the charge onto such a large conductor as Harrop, the potential won't rise very high. When he touches the terminal of the galvanometer, there will be no breakdown of insulation in the galvanometer coil. He must have been charged positively.
Calibrated in microamperes, a moving coil meter can measure the current from a Van de Graaff generator. You see, nearly 10 microamps. Now, a small Wimshurst may not be suitable for that demonstration. In this machine, the charge is collected by brushes which actually touch each sector in turn. So the meter would discharge each sector completely, but some charge ought to be left to induce more. In this bigger Wimshurst, the charge is collected across a gap, so it should be all right. In our teaching of current electricity, we rightly stress the conservation of charge in a circuit. In static electricity, the appearance of negative charge always accompanies the appearance of positive. My colleague Wenham is using the ionized air above the Bunsen flame to discharge the polythene rod and the perspex. Now both are charged, but with opposite charges.
With this arrangement of a deep can on the top of the electroscope, we have a measure of the entire charge on each rod and on the two together. The charges are not only opposite, but equal.
It would be a good thing if we can show this to be true in the more usual case where we rub the rod on a cloth. Again, we have to be careful about stray, unwanted charges. Insulating cloths like silk are too difficult to discharge in the first place.
On the other hand, woolen materials, which are good conductors, cannot be held in the hand, but they can be left within the can. This weight will serve to keep the material steady when I rub the material with this discharged rod. Yes, it is discharged. And again we show charge is conserved. The charges have all been rather small ones, and we have made our electroscopes more sensitive by using a very narrow leaf. This reduces the weight of the leaf and also increases the concentration of charge around the edges and at the tip.
Equality of induced charge is much easier to show. We need two insulated conductors and a charged rod. But instead of using the usual electroscope, I'm going to use this galvanometer again, with its sensitivity increased. Now, this experiment would give misleading results if either of these insulators were slightly damp. But a few seconds with a hairdryer will dry them. Of course, if they were really dry first, they may be charged now. But they're not.
Electrostatic fields can be displayed with the help of an EHT power pack and fine grains of semolina. In the dish, I have layers of castor oil and carbon tetrachloride. In between, the fine grains are floating. When I apply a voltage of about 3 kilovolts to the electrodes, the grains will make a map of the field.
There are other ways to show electric fields. This insulated paper vane, for instance, can be used to show the field between these two metal plates when we charge them with a Wimshurst machine.
With this large parallel plate capacitor, we can illustrate the concept of field in terms of the force experienced by a unit of charge placed at a point within that field. This glass spring supports a conducting sphere upon which I can place a charge. When I switch the 5 kilovolt supply on, the sphere moves. Now we can develop the idea that energy is transformed when charge is taken across the gap. But with this apparatus, we would probably be unable to show that the field within the gap was uniform.
The charge which was on that electroscope is now shared between them both, and both are at the same potential. The same thing has happened. But in this case, there was more charge on this side because of the stand and the can which I've added. And I can show that there's more charge by using my moving coil galvanometer again. About 1 centimeter, about 3 centimeters. An electroscope measures potential and not charge, but it hasn't got a linear scale. We should have to calibrate it by reference to some known supply. For example, this power pack and the moving coil voltmeter. That deflection corresponds to 1,000 volts. And again, of course, I can measure the charge which I put on this setup with the galvanometer. About 5 centimeters. This is a graph which we have plotted of the charge upon this setup, measured with the same galvanometer, against the potential to which the can and stand were raised, measured with a moving coil voltmeter.
A neat way of changing the capacitance is to lift a length of metal chain from a can by means of a nylon thread. As the capacitance increases, so the potential falls, and vice versa. Even my hand will show the same effect.
Sheets of aluminium foil and thick polythene sheet make excellent parallel plate capacitors. In fact, they can be more dangerous than Leyden jars. Perhaps I might ask my colleague to switch on, if you would. The meter here is showing us the charging current. It must be very nearly fully charged now.
That's very nice. Of course, most of the apparatus we have used in this film has been quite familiar to you. But perhaps we've used it in rather unusual ways. Some of the equipment can be obtained just up the road. The polythene sheet used by the gardeners, the aluminium foil used in cooking, the bathtub chain. Not forgetting the only use I've ever found for semolina.